Well, welcome back. As we start week 2, I want to introduce some cost and funding concepts, both to better prepare you for assignments coming up, but also there's information here that pertains to Dr. Robert Rosine's presentation for this week's Zoom meeting on Wednesday at 7:30. And there's also some information that's pertinent to the topic Kevin Geiger will be presenting in next week's Zoom visit. So in this presentation, we will touch upon what's called damage avoidance cost approaches. We'll be modeling infrastructure resilience costs and showing you how we did that through some research done here at Antioch. We'll talk about the difference between replacement versus marginal cost when making an economic argument. We are going to touch upon what we call depreciation timelines, or what is considered the durability of any built infrastructure on the landscape. And I want to just finish with an example of some work done around Keene about how to look at a potential remediation project and develop an economic argument that will allow you to get funding. I apologize, my clock just went off. So, just like others have seen around the country, there seems to be an increase in the frequency of more extreme weather events. Now, these events are occurring at a scale that exceeds the in-place capacity, or what we call the resilience of built infrastructure. Now, in the state of New Hampshire, it's become evident to every citizen in the state at some point in the past they have experienced this. Many of these storms were extreme events outside the historical norms. In this example, the rainfall amount had the likelihood of occurring in any one year. That's the percentage probability of 1/5 of 1%. And that's basically the 500-year storm. And we see this in other places across the state. This was Western New Hampshire in 2007, and Western New Hampshire again in August 2013. And because people are seeing warmer winters up here in the Northeast with more rain and ice storms versus snow events, the precipitation events don't necessarily occur in extreme amounts, but they still can be quite destructive. This is because instead of rain occurring in the spring, late spring or summer, and snow in the early spring and winter, the snow events, which melt slowly, we are now seeing more and more rain events in the late winter and early spring, and they're falling on frozen ground. And just imagine the runoff of falling on frozen ground. It is just like rain falling on pavement, and it runs off with no infiltration. And it can even be when the snow is gone. And this is known as the Mother's Day flood in eastern New Hampshire. The ground was still frozen in the forested uplands of the watershed. And so even though there was no snow down below, the runoff event from a non-extreme storm event caused amazing damage. And these trends of increased extremes and destruction that we see on the landscape, there's obviously a corresponding trend of cost. As can be seen looking at the federal expenditures due to the presidentially declared disasters. And we've seen sort of a bifurcation or a shift since the turn of the century, where there's a significant increase in damage cost that the government pays in reimbursements. But even these numbers are probably low because what the government pays for its reimbursements and what they don't is significant. And we will dive deeper into this when Kevin Geiger joins the class next week. Now, if we step back and just look at the larger trends, what the data is showing us is average annual precipitation has been increasing historically in the Northeast on the scale of 10 to 15%. And researchers have shown through a number of scientific studies, when one sees an increase in the mean or average and an increase in what we call the variation of events, there is a disproportional increase in the most extreme events. And we see this here, where the Northeast annual precipitation has increased on the scale of 15%, but the extreme precipitation events have increased by 71% over the same period. And this is a fourfold difference between annual average and extreme. And if we look whether these trends are projected to continue, the pessimistic future scenario, which is we continue doing what we're doing right now, as far as loading carbon dioxide into the atmosphere. In the northern United States, it is projected to receive more precipitation, especially in the winter and spring periods. Now, the areas with the red dots on these maps shows where projected changes are large compared to natural variations caused by other natural phenomena. Areas with the hatches shows where changes are small and relatively insignificant compared to natural variations. Similarly, extreme precipitation events in the Northeast will also increase on the scale of the Northeast of 30 to 40%. And even with the optimistic future where global temperatures are kept below 2 degrees centigrade, which is the goal of the Paris Accord, there will be increased impacts. So in this context, I want to cover a culmination over 10 years of research by Antioch researchers, both in New England sites and the upper Midwest. But for today, I'll just be referencing 3 of these, which are in New Hampshire. And I'm going to focus on the economic arguments being put forward that associate the scientific analyses. Now, the economic arguments being framed in these 3 studies are around not building resilience into a system. An example here, as can be seen in Keene, New Hampshire, where Antioch is based. In 2005, an extreme precipitation event caused damage to the drainage system and associated road. It was approximately $8,000 in cost. Well, the city repaired the damage with the help of some federal funds. But because they used the federal funds, they were required to replace the obviously undersized drainage system to the same size and specifications. Well, 7 years later, it happened again, but the damage costs were significantly higher, again due to the undercapacity resilience of the drainage system. Now, the overarching take-home message is to understand the incremental cost, what we call the marginal cost of building resilience into built infrastructure, compared to the costs of such infrastructure failing. So this argument is known as a damage avoided cost strategy. An equally educational example, building resilience into water conveyance infrastructure versus the cost of damage occurred, came just after we completed a study in Southwest New Hampshire for the Ashwillet River watershed. Just 1 week after we reported out our results, a 500-year storm event, that's 13 inches falling in 24 hours in this region, hit the watershed. Now you will note that the damage costs were approximately 100% greater than the marginal cost our study projected of putting in at this location a stream crossing of adequate size to meet the amount of runoff created by such an event. And in fact, the Federal Emergency Management Agency, FEMA, has collected data over time to show that it is typical to see damage costs being 4 times the cost of building resilience into infrastructure. And speaking about FEMA here, for this location, they only reimbursed about 30% of the damage cost. Again, we will learn why this is occurring when Kevin Geiger joins us next week. So, our research focused on assessing the vulnerability of communities' water conveyance infrastructure due to a changing climate in the context of a changing landscape. In short, we were looking at culverts' capacity to pass peak flow of runoff. Now, why focus on culverts? Well, it introduces easy to understand discussion of land use, increased runoff of water, and projections about the future. And culverts are easy to field check and measure so that we can test the models we're using. And culverts have a tangible dollar value attached to them that can be used to do replacement and mitigation cost analyses. So for our study, infrastructure adequacy, that is whether a culvert was properly sized, either for historic or future precipitation events, came in 3 designations. One was it was adequate, okay, which means it was in weir flow that at the peak flow, water could get through the culvert. Then we had what we call close to orifice flow. This was transitional, where the peak flow completely filled up the culvert and there was not any margin for additional runoff. And then there was orifice flow, where the pipe was undersized for the amount of runoff and water basically started to back up. You see this little picture here, that whirlpool, there is actually a culvert 4 feet below that. Now, there's going to be associated cost impacts from undersized culverts, both related to up and downstream property damage, either from flooding, erosion, sediment deposition, or sediment transport further down the watershed, impacting natural systems as well as built infrastructure. Now, of course, we as scientists always make things a bit more complex, but in essence, we are using well-tested approaches in these studies to build a view of the current and future infrastructure capacity and associated costs. The analysis of changing precipitation patterns was looked at, considering also a changing landscape, that is, putting more impervious surface on the landscape, to first determine, was the current culverts in place vulnerable or resilient? We would use off-the-shelf hydrologic models to provide the outputs, and the outputs was assess the capacity and resilience of the current infrastructure, and from this analysis, understanding system resilience. And we could consider response options such as upsizing systems for the expected flows, that is, making larger culverts or stream crossings, and also how we might mitigate the impact in this case by building out the watershed utilizing green infrastructure. And this is what Dr. Robert Rosine will go more in depth to and provide cost analyses of what that means on Wednesday. So let me use one example of how one would pull together the various pieces to conduct a vulnerability assessment and the associated cost impact analysis. This is a multi-year study we did that was funded in part by NOAA in the Lake Sunapee watershed. You can see that watershed had a lot of micro watersheds in it. And so we were looking at approximately 210 infrastructure choke points. Now this example of our outputs was called a stoplight map, red being undersized road crossings, stream crossings, green adequate, and yellow are at 100% of flow capacity, which are transitional. So we were able to identify specific locations of undersized culverts to the peak flows of stream and road crossings, both historically and projected into the future. Now, the future scenarios not only looked at projected precipitation from a changing climate, but also considered increased impervious surface within the watershed due to projected development patterns based on master plans and zoning ordinances. Thus, they provided land use planners about places not only where the culverts were possibly in need of replacement, but also what parts of the landscapes where they may curtail development or enforce mitigation measures. Now, doing the associate economic analysis, we use national construction cost estimators, such as means construction tables, to estimate cost replacing each size culvert with one adequate capacity for any future projection. So pricing schedules were developed for each culvert size and type. And you can see that this looked at labor costs, materials costs, design costs, etc. Now, we ground truth these culverts by going out with the local DPWs to see where they had already seen such damage. And then we extrapolated to the entire basin for specific culvert sizes based on our cost estimator pages. So for one sub-basin, okay, the White Brook sub-basin, you'll see, using our construction cost estimators, we were able to come up with a total cost for different size culverts that needed to be upsized. Now, if we extrapolate this one number based on the culvert sizing to the whole watershed, you know, we could see a $2 million increase in expenditures to make all culverts resilient. Now, another study looking at the same dynamic, but this was a coastal watershed that wasn't as flashy, you know, only a 400-foot elevation difference between top of the watershed and where the stream emptied into the ocean. And in this coastal watershed, there was one thing different than the Sunapee watershed is that there was a lot more build out. That is, the watershed had been built out a lot more, so there was a lot more impervious surface. And interesting enough, the outputs, again, these are cost of replacement. The first column is the replacement cost for a number of different culverts. The codes are different micro watersheds. The subsequent columns are replacement, but upsizing the system to meet the increased runoff coming down the watershed due to increased projected precipitation events based on climate modeling. Now, what needs to be realized is that all the culverts have to be replaced at some cost. So the true cost to consider is what we call the marginal cost of upsizing, because they do have to be replaced. And the marginal cost of upsizing is the additional cost of putting resilience into the system to meet extreme future events. So if you look at this table, and you look at the first row, the difference between $5,164 to upgrade the cost for an increased runoff event versus the $3,474 here, which is basically just replacing it in kind. The difference is $1,690. So this is the marginal cost, $1,690, to put more resilience into the system for increased precipitation events using the most optimistic future. But another interesting result was, you'll see for the first 4 culverts here, that the marginal cost increase puts enough resilience in the system to deal with the most pessimistic future. So just upgrading for the optimistic future, there's enough resilience now in the culverts to deal with the runoff coming from the most pessimistic future precipitation event. Now, why is that? Well, one thing is, you must realize that culverts come in fixed diameters, like 16, 18, 20, 22, 30-inch diameters. And so just increasing the diameter by 2 inches, because of the mathematical relationship of diameter and thus radius to area, one incremental increase of 2 inches in a culvert diameter substantially increases the opening to allow more flow. So our research was pointing to what we consider a rule of thumb. That is, that if you took a no regret decision and increased all your culverts by 3 increments, that is 6 inches in diameter, then you basically would handle the worst case future scenarios of both build out of the landscape and creating more impervious surface and the most pessimistic precipitation amount. Now, let's drill down a little bit in the study. If we look at the impact to one small town in the study area, and summed up the cost of bringing their infrastructure up to the size to meet even the most pessimistic future precipitation scenario, the upgrade costs are approximately $168,000. Now, this may seem a lot of funds for a small town. And if this total cost were the focus of a communication to the citizens in order to get their approval to expend this sum, it may see quite a bit of opposition, especially for something that is uncertain in regards to future weather. So it is important to reframe the cost argument so to put this replacement cost in perspective. So for this town, consider the $168,000 upgrade cost is approximately 1.6% of the $10.5 million annual town budget. And this budget is based on a property tax being charged to homeowners of approximately $26.76 per $1,000 assessed value of the property. So if all the underside culverts were replaced in a single year, this would increase the tax rate to $27.18 per thousand. And this is actually only an increase of 42 cents increase per $1,000 of property value. So this is a bit more palatable for citizens to accept. But we can go further. If we could use the time value of money That is, if the town could amortize this $168,000 over a 15-year bond at a 2% interest rate per annum, the town's annual payment would be approximately $12,000 or $13,000 annually. And that's an increase over what they're doing today. And based on the tax rate of 2676, the annual bond payment would add approximately 3 cents per $1,000 assessed value for the next 15 years. Now, if we were to communicate this building of resilience into the system in this manner, there probably would be very little opposition due to this small incremental annual tax cost. Now, we will be addressing bond financing in more depth during the last week of the course. So, take-homes here so far are all infrastructure has a depreciation or durability life on the landscape. So if the life is long enough to be impacted by future shifts in climate parameters, it may be wise to build resilience into the system. And realize once any built infrastructure is put on the landscape, there will not be a lot of political will to subsequently replace it, so to add additional resilience, or at least until it has run the course of its durability life. The cost of building more resilience into the system must be viewed as a marginal cost, since the infrastructure has to be replaced at some time in the future. And finally, by not expending costs to build resilience in today, the future damage costs could be significantly higher. Now let me just finish with one final small study that was done here in Keene, New Hampshire. That is how to leverage funds available to build resilience into water-conveyed infrastructure or into any infrastructure. And this approach is called competing for funds using a co-benefit approach. So beyond just looking at peak flow in the Keene area, one could look at culverts based on what we call their geomorphic capacity. That is, were the culverts placed on the landscape in a proper way with a proper sizing that reflects the natural energy of the landscape that basically carves and creates the topography we see. And as you see from this, at different elevations, there are different stream configurations as the slope changes, and you see an increase in carving and meandering patterns. The stream wants to do that, and if you put in a system that doesn't allow it, it will do work to try to get back to what we call the stasis of the system based on its location on the landscape. So, if you do not do it, this is what you will see. You'll see basically the natural system will do work, and primarily that work is carving and moving material until it has the equalization of energy, and you have somewhat of a steady state. So you can model culverts for geomorphic assessment. And many state planners want to see that kind of analysis because they want to avoid extended damage, not at the road crossing, but extended damage along the whole corridor of the stream because of the possibility that the road crossing is not in line with the energy of the system. Another perspective of the same system would be what we call aquatic organism passage. That is, are road crossings and culverts allowing passage of species such as fish and associate species such as mussels, which attach to the gills of fish. And we know that aquatic passage, there are different problems for different species depending on both the velocity of water as well as the ability to pass through the culvert. So does the culvert include the ability for passage during low flow depth? That is the culvert at its outlet so high that species can't get over it? Is the water coming through it so strong that basically species can't swim up against it? This is just one study comparing two culverts, and the basically the perch culvert on the left basically had a very high perch, very high jump, and this is basically looking at tagged fish, in this case brook trout and brown trout, the ability to move up through aquatic organism passage. And obviously the perch culvert had much less passage. And if we look at the same system on what we call a landscape scale, and conservation biologists call this looking at metapopulations, this is basically an example of connected stream networks in Massachusetts, okay, with major dams that basically constrict the ability of connectivity of populations. And then if you add undersized culverts, you can see that the length of connectivity is reduced dramatically. And so if populations become fragmented enough, because of dams and culverts, populations within a constrained length of stream could die out, be extirpated because of some event, either land use or natural event. And they are not likely to return until that fragmentation is removed. So we have three analyses of the same systems, okay? We have first our culvert flow status, that is our peak flow status that we were talking about in the previous studies, whether they're adequate to move slows. And this is basically a micro watershed in Keene that we did the analysis for. Then on top of that, you can do a geomorphic analysis. Are those systems also geomorphically compatible with what they should be based on where they are in the watershed? And obviously in both these models, reds are no, greens are yes, and the lighter colors they're in transition and they could be at risk. So there's the geomorphic, and then we can compare our peak flow with aquatic organism passage. And again, we get, the reds and the greens and the lighter colors of showing whether the crossings are adequate or not. And if we put these three together, and so look at them and sort of see which ones meet all three criteria, that is, which are undersized because of peak flow, because they're not set right because of geomorphic compatibility, and they basically will not allow aquatic organism passage, we can basically narrow down to a subset of culverts that meet all three criteria of being undersized. And in this example, we were going after U.S. Fish and Wildlife funds to enlarge the culverts. And we were competing against a number of other potential funders in the Northeast. And we won those funds because we made an argument that showed the co-benefits of the culverts. And even though the U.S. Fish and Wildlife Service was only interested in aquatic organism passage, by showing the co-benefits, we basically acquired the funding to basically upgrade these culverts. So this is just one way to sort of use co-benefits to make an argument to capture funding that's out there. So I will leave you at that, and we'll talk to you again on Wednesday when Robert Rosine um,